Yes, sir, we are live.
Okay. Good afternoon, everybody. This is the last speaker today in the last session, Dr. Naveen Shetty from Brussels. He is going to give his lecture on structural health monitoring of bridges. Sir, you know this. This is a commemorative lecture of CEG Gesto on behalf of one first death anniversary of this legend. So we are conducting this workshop. Already, you must be knowing this. There are 500 speakers. Sorry, 500 registered participants, and few of them from abroad. Apart from that,
Yes, sir.
there are speakers from abroad, and one such speaker, Dr. Naveen Shetty. Thank you for joining here, sir, today. And
Thank,
it will be on structural health monitoring of bridges. Before we start, now I'd like to introduce Dr. Naveen Shetty. Dr. Naveen Shetty is from Bangalore. He did his engineering in Dayanand Sagar College of Civil Engineering, and then went on to do his MS in Germany. From after doing his MS, he went on to do his PhD program in Brussels, Leuven University, and it's one of the prestigious university. He finished it, and he is now structural health monitoring of bridges is one of his favorite topic. So he's going to give a lecture on it. Thank you for joining, Mr. Dr. Naveen Shetty. Now you can proceed. Sir.
thank you, sir.
Thank you very much, sir.
So a very good afternoon to everybody. Welcome to the presentation. Today I'll be talking about structural health monitoring of bridges. First of all, I would like to thank all the staff members of CTM department, Dayanand Sagar College of Engineering and also especially for Professor Prakash sir for inviting me and for giving me this opportunity to deliver this webinar in this workshop. So firstly, I will introduce myself. My name is Naveen Shetty, and I obtained my bachelor's in civil engineering from Dayanand Sagar College of Engineering in 2012. And then I went to Germany and I pursued my master's in structural engineering. And in 2015, I graduated from Bauhaus University, Weimar. And very recently, in 2019, October, I received my PhD in civil engineering from KU Leuven in Belgium. And during my PhD, I was also a visiting research scholar at UPC Barcelona. And also this year, from the beginning of this year, I've been also worked as a postdoctoral researcher at KU Leuven in Belgium. So as a structural engineer, my mission is to promote more of the scientific values of the building performance. Therefore, my research field includes seismic analysis, especially with relation of masonry structures, development of finite element models using different commercial softwares, and also I've been working on NDT methods where I'm using different type of acoustic emission sensors and also digital image correlation on all these new advanced methods for monitoring crack progress in structures. So today I'll be delivering some of the following topics in this webinar. So firstly, I will talk about the failure of bridge structures by presenting some real scenarios of why there are many bridge structures which are failing nowadays. And secondly, I will talk about what is structural health monitoring, why have to or how is it very useful for structural engineers, and also what are the monitoring process in them. And thirdly, I will also discuss about some of the structural health monitoring methods for bridge condition assessment. So there are many monitoring methods, and have chosen some of the three major solutions for condition assessment of bridges. And lastly, I will talk about the future of structural health monitoring. So in that, I will also talk about the benefits of SHM and what are the challenges nowadays, and also the recent advancements of structural health monitoring. So we all know that bridge structures represent significant proportion of traffic infrastructure. So in earlier days, bridges were usually constructed by using uh, very normal available materials like the globally available resources such as bricks, blocks, and also lime and cement mortar. and they were designed only for very short span length. But the greatest revolution came with the development of industrial sector, where a large amount of volume of the traffic increased, and also there were the weight of the vehicles also increased. So the steel truss bridges came into existence, and this was given main priority of using steel bridges because they could cover larger span, and also they could resist the heavy weight. Another important innovation is the suspension bridges. They are they can really cover the very large span length, and also they can avoid any intermediate interaction, so they don't have any intermediate structures, and they can cover very large span lengths. So this was one of the very innovative solution in bridge engineering. So with the modern developments in concrete technology industry, by embedding the steel into the concrete, so post-tensioning and pre-tensioning concrete bridges have been also widely used all around the globe. So what about the failure of bridge structures? Why there are so much failure of bridge structures? So the bridges are often prone to damage or failure because of the live loads acting on it. So these are considered as the physical loads, especially that also includes the high traffic density and also overloading of these structures. And the other loading is also about the environmental loadings, which is always subjected to bridge. So the environmental loading are the wind, rain, extreme heat, storm. So these parameters also affect the bridge structures, and the bridge structures are always exposed to environmental or different weather conditions. So all these parameters have a negative impact on the load bearing capacity of the bridge structures. So I would show you some of the real scenarios over here. So this is the first, very recently in 2018, the bridge collapse of Morandi Bridge in Italy, which was a very highly major disaster, which killed almost 43 people and many were severely injured. So the latest reports indicate that this bridge was exposed to air pollution, which was very close to nearby industries, and also it had a salty, like sea salty air. So this led to corrosion development in the bridges, and the inspection was not properly performed, and finally, it just a 200-meter section of the bridge collapsed. So this is one of the major disasters that happened, and it indicates that what we learn from this incident is that the disruption to the traffic infrastructure can have a tremendous impact on the economic growth and also for the daily life of the citizen. So very recently this year in April 2020, another bridge collapsed in Italy, and due to coronavirus pandemic force, since there was a lockdown over here also in Italy, so there were not many people traveling on this bridge during the time of collapse, and two people were injured from this incident. And also the reports indicates that there were very major cracks developed in the pavements of this bridge, and also it was reported to the building inspection people to have a look about these cracks, but they I think very recently, maybe last year, they reported that it was not a major cracks and it could be neglected. But on 8th of April 2020, the bridge completely collapsed. So this revives again the memories of Morandi Bridge, which happened in 2018, and it also alerts the worldwide to everybody that there is a need for or requirement for immediate attention towards the existing bridge structures all over the world. And this is very recently, like just 3 days back, a bridge collapsed in Uttarakhand. I would play a short video clip of this. So we see that the main reason for this is this collapse is because of the truck which was carrying a construction equipment. So there was a combined weight, and that weight exceeded the load bearing capacity of the bridge. So that caused the failure of the entire bridge. So now the golden question is, how do we ensure the safe working condition of bridge structures? In other words, how can we monitor, or how can we prevent such failures of bridge structures? So I will relate this to a medical procedure. Normally, when we have a bone fracture, we visit to a medical care center. So the doctor performs some of the preventive measures that includes lot of tests and screenings, where the doctor tries to locate or indicate the the initial the damage or something at a very early stage, rather than it becomes a very bigger problem. So we can take this concept into in our civil engineering context, and we can treat the any structures, but here I'll say the bridges as the patients, and we the structural engineers as the doctors, and to use some of the diagnostic techniques in order to identify the problems at a very early stage. So here comes the structural health monitoring into picture. So what is structural health monitoring? It is a diagnostic methods which are used on the structures in order to provide some important information about the structural performance. Nowadays, there are also very advanced structural health monitoring methods which can also provide us very early warnings even before the damage is foreseen. We can already locate the damages or the intensity of the damage that is happening inside the structure. And SHM includes a wide range of sensors and also wireless communication, and it is monitored continuously. So that is known as the real-time monitoring. So it's continuously monitored uh, like 24/7. And what is the goal of structural health monitoring? So firstly, it is to detect the damage based on the measurements, and secondly, to locate that damage. So in other words, in order to locate the geometric position of the damage, and thirdly, to quantify this damage. So if we know the detection location, and if we also quantify the damage, we can already know the critical condition of the bridge structure. So this slide presents a representative picture of a bridge with a typical structural health monitoring layout for bridge condition assessment. So structural health monitoring, as I said, it includes a array of sensors deployed at different positions of the bridge elements. So here we see there are different type of sensors like acoustic emission, wind speed, temperature, and strain gauges, and they are deployed at different respective positions of the bridge. As we see, the wind speed, it's usually positioned at the top of the column element, and the temperature is usually deployed at the midsection of the bridge deck in order to monitor the temperature changes. And the strain gauges are usually deployed at the underneath the bridge deck in order to measure the deflection. And acoustic emissions, they are nowadays usually deployed in the critical zones of a structure, especially in the cables and also in the piers, deck, anywhere. So it's very advantageous method, and I will be discussing about it in this presentation in the later slides. And this slide presents the monitoring process of the structural health monitoring. So as I said, there are different array of sensors. So the wind sensors, the temperature sensors, the strain gauges, the acoustic emission. So each sensor has its different functionality among them. So the data obtained from all these sensors are integrated together, and they are further processed, and that is known as data fusion. Data fusion is the integration, collecting or gathering the information, collecting it, and integrating them together. And the data fusion is further passed to a cloud storage, or where we maintain the large amount of data, and Usually now we use the cloud storage platform where we store the data over there, and then we use certain type of SHM softwares in order to perform further analysis. So based on the performance of the analysis, we we conduct two other parts, that is reporting and alarming. So reporting is conducted, and based on that we are taking the further decision whether alarm has to be generated or not. So this is the process flow for structural health monitoring. Now this is the major question: how can structural health monitoring help structural engineers? So firstly, structural health monitoring gives a very rapid solution. That is, it gives us an instant information about what's happening in the structure, and it also reduces the inspection time. And secondly, structural health monitoring can be easily customized. So we can adopt structural health monitoring to any sort of bridge elements or any type of bridge elements. Another important aspect of SHM is it is repeatable. So in this case, it helps the structural engineers to monitor the bridges for a very long time. So we can also inspect the bridges and we can look at the maintenance of the bridges for a very long time. And also it gives us or gathers us a lot of information during this period. And the information is very related to the structural performance that includes structural integrity, or the aging or the deterioration of the bridges and so on. And lastly, structural health monitoring saves money. Yes, it's a one-time investment, and if we compare it with the frequency of the site visits that a building in or a bridge engineer has to do in order to inspect the structure, SHM initially there might be some expensive, but for a if you see for a long run, it saves money. And what data can be gathered from structural health monitoring? Since structural health monitoring is an array of sensors and each sensor has its different functionality, so the following informations can be obtained from SHM. So especially the stress, strain, the deflection, and the inclination can be obtained from the strain gauges that are usually deployed at the deck of the bridges, and the vibration can be obtained from the accelerometers. The crack progress, and even nowadays the corrosion can be also detected by using acoustic emission sensors. So in recent advancements, SHM has really, there are new sensor technologies and also the wireless communications which are giving us new developments in SHM method. The three major solutions for real-time monitoring of bridge conditions are vibration-based monitoring, strain-based monitoring, and acoustic emission monitoring. So in the next slide, I'm going to discuss about the vibration-based monitoring. In vibration-based monitoring, we have to evaluate the dynamic characteristics of a bridge. So in structural mechanics term, the modal parameters are basically the natural frequencies and mode shapes. So since the modal parameters are very much related to dynamic characteristics of a bridge, it's easy to note that the location and the severity of the defects by conducting some of the simulations as well. And also we can perform this analysis based on the acceleration data that we obtain from the bridge. So here I have shown you one of the example, and also it's from our department here in the University of Leuven, which was conducted on a bridge, a monitoring on the bridge, and based on the vibration response, different mode shapes were developed, and based on the mode shapes, we could identify the location and the severity of the defects in the bridge. So in order to perform vibration monitoring, we need to, or to also know to study the dynamic characteristics of the bridge, we need to know the vibration measurements. So this is basically conducted in two different types. So that is the ambient vibration and the forced vibration. In ambient vibration, usually the bridge structures are, it's natural, they are subjected to vibration because of the movement of the traffic, also because of the wind, and also maybe due to seismic excitation. All these terms are considered as ambient. But in practice, now before opening it to traffic, we need to perform a controlled load test. So in that scenarios, we perform where, as shown in the first picture, the trucks are passed over the bridge, and these trucks are, they have calculated the bearing capacity of the bridge and the truck, and they perform the movement of the truck over the bridge at different speed levels. So this creates some of the excitation sources, and that is known as the ambient vibration. And whereas for very smaller bridges, the sledgehammer is enough to create the excitation of the vibration. So that is known as the forced vibration. So we need to measure the vibration which is developed in the bridges, and for that we use very simple sensors known as accelerometers. So accelerometers are the piezoelectric transducers which generate electric charge when it is subjected to a uh, mechanical pressure. So accelerometers are usually deployed at the different positions in the bridge, especially as I said before in the deck of the bridge, as shown in this picture. And they usually measure the vertical and horizontal accelerations that are coming from the vibrations. And they are very sensitive sensors, and they are very sensitive to dynamic motions or vibrations. And based on the design of the sensor instrumentation layout, in other words, the distance between each of the accelerometers, it depends on again the span of the bridge. Based on this deployment, we can also determine the severity and also the location of the defects. So the vibration based monitoring, as we know, it's basically to study the dynamic characteristics of the bridge, and it's on a very global level. So there is a need to know what is happening at a local level of the bridge. So here the strain based monitoring comes into picture. So in the next slide, I will be talking about the strain based monitoring. In strain-based monitoring, usually the strain gauges are deployed uh, at the critical locations of the bridges in order to monitor the bridge elements. So the main focus of using strain gauges is to record the displacements or the deflections of the bridge deck at various locations. And strain gauges are the most popular sensors that are used widely nowadays. And also nowadays, wireless strain gauges have come into existence. So strain gauges usually they contain a foil within them, and when there is a external force applied, the foil gets deformed and the electrical resistance changes, and this can be measured. So that's the main working principle of strain gauges. And they are usually deployed on the surface of the structures in order to measure the surface defects. And there are various types of strain gauge sensors, like the linear variable differential transformers, vibrating wire transducers, inclinometer, and fiber optic sensors. So linear variable differential transformer, as the name itself indicates, it is used to measure linear displacement between 2 points. Linear variable differential transformer is an electrical transformer, and it can convert the linear displacement into a corresponding electrical signal. And vibrating wire transducers are normally the steel wires, but they have behind concept which works on the resonance frequency of the vibration. And inclinometers are usually positioned at the cross joints of the piers and the deck, and it is used to, and these sensors are used to measure the inclined or the angle of flow in relation to the gravity. And lastly, the fiber optic sensors, which is presently in a very great development and also have been widely used in civil engineering applications. They are basically used in bridges as well in order to measure different parameters such as the pressure, humidity, temperature, strain, and also vibrations. So these are some of the strain gauges that have been deployed in the bridge in monitoring of the bridge structures. So up to now, we saw that the vibration-based monitoring was on a global level, and it was mainly to study the dynamic characteristics of the bridge. And we saw the strain-based monitoring, which was applied on a local condition where to measure the deflection or deformation. So basically, the mechanical properties of the bridge. There is a need to know what is happening within inside the bridge structure. So acoustic emission comes into picture over here. So this technique is mainly based on elastic wave propagation. So we pass the elastic waves into the structure, and based on the wave propagation, or by analyzing these waves, we get to know what is the structural integrity uh, of the monitored section. So acoustic emission is a unique monitoring method because it can identify also the geometric position of the damage even before the crack is visible to the naked eye. So the working principle of acoustic emission is as follows. When there is a micro crack in the material, so the strain energy, the localized strain energy, is released in the form of a elastic wave with a sufficient amplitude, and that amplitude or the elastic wave with sufficient amplitude travels in the material, and it reaches the nearest transducer that is deployed onto the surface of the material. So this is basically the phenomena of acoustic emission monitoring. And here the transducers are usually referred to as acoustic emission sensors, are usually glued or used some kind of petroleum jelly on the surface of the sensors in order to attach them to the structures. And the sensor, what it performs is it takes the mechanical energy carried by the elastic waves into, and it converts it into electrical signal. So the electrical signal detected by the sensors are then passed into the amplifiers. So the amplifiers, they register these electric signals, they filter them and they amplify them, and then further proceeds it to the acquisition unit. So the elastic or the acoustic emission waveforms which are received at the acquisition unit are further analyzed to derive more information about the fracture mode. So this is the total procedure of acoustic emission monitoring. Also, in practice, the acoustic emission monitoring has two types of sensors. That is, one is broadband sensors, and the other one is resonance sensors. So, resonance sensors are quite sensitive at its resonance frequency, and broadband sensors are less sensitive compared to resonance sensors. And another major advantage of using acoustic emission monitoring as an SHM is that it produces enormous amount of audible frequency, which is audible to human ear, the sounds during a crack propagation. So this act as a alarming system as well, or a warning system before the structure is prone to collapse, or before the structure has a very major damage in them. They can also act as a warning system. So as I mentioned before, the received waveform in the acquisition unit is further processed. So this is the typical AE signal as shown in the first picture. So what we do is we there are certain parameters which are already defined for this signal, and we analyze those parameters in order to find, or in order to determine what are the fracture modes. So this is not very straightforward approach. It involves a lot of analysis, algorithms method uh, within the post processing unit. So over here, you see that the threshold which is assigned over here is basically to avoid the background noise, especially the deployment of acoustic emission on bridge structures. Uh, Due to environmental conditions, there are also chances that it takes the noise from the background, and it's very hard to differentiate them from the true sources. So we always set a threshold value in order to eliminate such background noises, and for that we also have to do a calibration test before bringing them into the practice. As I said before, acoustic emission is not a straightforward approach. And there are two different methods in order to analyze acoustic emission data. That is acoustic emission parameter based approach and acoustic emission signal based approach. So the difference between these two analysis or the approaches is that it's only based on the collection of the data, the gathering of the data, and the procedure deployed for different analysis techniques. So basically, the difference is that the way you collect the data and how, what is the procedure you consider for analyzing them uh, in order to determine the condition monitoring of bridges. So in the next slide, I will present you some of the case studies or the on-site applications of acoustic emission on for condition monitoring of bridges using AE parameter based approach. So the first application of acoustic emission for monitoring of reinforced concrete and masonry bridges was conducted by Shikeshi, and this developed originally emerged in Japan, and even nowadays they are widely used in Japan for in situ monitoring. So the work defined in this article is that the bridges had already had been some of the damages, and in order to know the service condition of these bridges for modern traffic, so the monitoring had to be performed. So as you see in the above pictures, the acoustic emission sensors are mounted beneath the bridge deck at sufficient distances. And also the other important thing is the bridge was not closed during this monitoring technique, and the movement of the vehicles or the traffic loading becomes the source for the signal excitation. So it was a very interesting article since it's the old one, especially for the application of acoustic emission, and it already revealed that acoustic emission can detect the position of the crack even before they are visible to the naked eyes. So in the result, we can see that the X position is the position of the acoustic emission sensors deployed in the bridge deck, and we see the events. The events are the obtained acoustic emission or the detected acoustic emission, which are arriving from the internal structures. And we see between the location sensors of the 1 and 2, there is a localized peak. And also after this process, they saw that there was a crack in that position. So the conclusion from this paper was that we could already see we could already sense the position of the geometric position of the crack even before they were visible to naked eyes. Sorry. Especially in United Kingdom and also in Europe, there are many bridges, especially masonry bridges, which are over 100 years old, and all these bridges require monitoring methods because of the current traffic density and overloading. They are already subjected to cyclic compression, and that has developed a large number of cracks in these structures. So the work presented in this paper was something similar, but over here again the acoustic emission was deployed at this the arch shape of the bridge, and here the during monitoring the bridge was closed, and before strengthening and after strengthening there were two types of monitoring process performed, and before strengthening was the current or the at that moment the situation of the bridge, and we could see that the acoustic emission from the results that the acoustic emission produced a lot of amplitudes at, during the dynamic loading condition. So before strengthening and after strengthening, the control tests were performed on the bridge. That is, the truck was passed onto the bridge and at different speed, and the emissions were recorded. So what they observed here was after strengthening, as shown in the below figure, that the AE activity reduced significantly. So the amplitudes was very low, and this indicated that bridge has been strengthened and there were not much of any cracks in them. So up to now, we saw that these were some of the parameter-based approach for the application of acoustic emission as a SHM for bridge condition monitoring. So in the next slide, I will present just one on-site application where they used AE signal-based approach in order to perform the condition assessment of bridge structures. So over here, this work indicates that the acoustic emission sensors were applied at the bridge piers, which was already damaged, and that supported the railway bridge, and it had been damaged because of the seismic excitation. So the sensors were like randomly distributed over the reinforced concrete pier, and the monitoring was performed based on the train movement. So the train passed, and there was some signal excitation which was received in the acoustic emission sensors. So over here, we need to see that they applied broadband sensors, and because it's a signal processing, and they also applied a wave propagation algorithms in order to locate the geometric position of the sources. So in this picture, you see the round plots. They all are the acoustic emission sources, which indicates that that's the critical position in the structure, which needs to be replaced or that needs a retrofitting in future. And this is not a straightforward procedure again, because the source location algorithm which is implemented has to be redefined based on the heterogeneity of the material. And also the acoustic emission sources was found to be spread all over the region. And that is because, again, because of the algorithm procedure, it's very much related to the velocity of the waves within the structures. So we saw both the type of approaches here as a SHM system for the bridge monitoring, but there is some limitation for the application of acoustic emission onto the bridge structures. The reason is acoustic emission has, since it takes the emissions from the integral part of the structure, there is also a possibility that it can collect noise. That's the background noise. And also, depending upon the material, especially for steel, it's very applicable because steel is very homogeneous material, and for steel bridges it is excellent. And for concrete bridges, yeah, we need to play around with the different type of sensors based on their frequency levels in order to eliminate the attenuation and all these wave propagation properties. Whereas in masonry structures, it's quite complicated because masonry bridges or the masonry structures have huge kind of heterogeneity in them. So this is where the signal damping appears, and this hinders the reliable analysis of the data, and it also never gives a very accurate interpretation of the result. So this is where my PhD comes into picture, and in this PhD I have developed new and also a very different approach in order to characterize or in order to um, eliminate such signal damping methods. So, extensive laboratory tests were performed on masonry samples by applying some of the cyclic compression tests. You may ask me why cyclic, because this is more relevant to the masonry bridge structures. Especially in bridges, the loading is performed in a very cyclic way. So that's why we performed a very cyclic load was applied on the masonry structures, and developed a new concept of load and calm ratio for the first time in masonry structures. So over here, I also have proposed some of the critical damage limits that differentiate, as we see in the picture on the right hand side, the corner picture. It clearly differentiates the damage into minor, intermediate, and heavy damage. So this is still at a laboratory level, but we can apply this methodology on the bridges, and we can also characterize the load or the damages appearing on the bridges into a minor, intermediate, or a heavy damage. So if you want to know more about the background concept of this methodology, then please feel free to go through my PhD thesis. So up to now, AE monitoring has been a very reliable one, and also it has a very good application in SHM methods. for monitoring of bridge conditional assessment. And also, I know that especially in Europe, there are many companies which are already applying AE monitoring as an SHM system for monitoring bridges, especially steel and concrete bridges. So as we saw from all these SHM methods, based on the real-time monitoring, that is the vibration-based method, the strain-based method, and also from the acoustic emission-based method, by integrating all this together, we can have some of the benefits. First thing is continuous remote online monitoring. As I said before, and also showed you some of the examples, um, the traffic is uninterrupted. Also, so that means that it can be monitored continuously, that is 24/7. And detection of non-visible defects. Here, acoustic emission plays a major role, where it can already detect the defects before it is visible to the naked eye. Uninterruption to traffic. Yeah, as I said, the bridge need not to be closed until it is in a critical condition, but it can be ongoing when the monitoring is performed. Reduction of inspection costs. As I said, SHM is a one-time investment, and it drastically reduces the maintenance costs, especially with regard to the frequency of bridge inspection by the bridge inspectors, uh, which is usually performed. Prioritization of repair or replacement. So by deploying the sensors different positions, we can already, and also different sensors are deployed which has different functionalities. We can already receive enormous amount of data and information from this, and we can already make or prepare a further decision regarding the critical condition of the structure, whether there needs to be a repair or replacement of the critical elements. And lastly, the application of structural health monitoring um, increases the confidence in structural integrity and also in public safety. So these are some of the benefits of SHM. Even though we know that the SHM has many advantages, but there are still certain issues to apply them onto the real practice scenarios. Uh, why we are not still using it, especially for monitoring bridges? So the first thing comes is the cost of SHM systems. Yes, they are very expensive for the initial stage, but later on, if you compare the SHM cost with the other cost or the building inspection cost, uh, if you look for a future, it's a very in the initial stage it's very expensive, but in the later stage it compromises, and they don't have to do a regular inspection for the bridge structures. And secondly, the type of sensors to apply. So this always remains a confusing task for project engineers and bridge engineers in order to decide which sensors have to be applied. So the major or the important thing over here is to apply a very good array of sensors. So we need to know what is the damage that is applicable in the structure, and which type of sensors can deploy or which can provide us a very reliable and enough information. So based on this criteria, we need to select the sensor type. And thirdly, the installation of SHM system. Well, the applied SHM system nowadays are mainly based on wired systems, and the installation of the wired SHM systems are very expensive because of the labor intensive, and it's also time consuming, and also there includes cost. And lastly, the interpretation of results. So we saw that there are different array of sensors deployed, and this provides us very large amount of information. So the collection or the gathering of the information, the analysis of the information, and the further decision or the interpretation of results that needs to be taken is a very complex issue. So a very skilled person has to be taken into consideration for performing the last process, that is the interpretation of results, because he has also need to know what is the further decision that has to be um, that has to be given in order to provide the condition assessment of the bridge. And next thing is the future of SHM. So presently there are wireless sensor networks without any wired networks that are being recently being developed, and also there are some of the micro electric mechanical systems which are very prefabrication of sensors that are used. Especially these sensors are deployed into the concrete nowadays when they are manufacturing the bridge itself, so that they remain there for lifetime and they gives us the information throughout 24/7 and throughout the lifetime of the bridge. And the next thing is the cloud-based approach that is nowadays, which is a very booming thing of Internet over things. It's a cloud storage, and all the data, or including the raw data, is dumped over there, and then the process takes place, and it also does not require that you need to come to office in order to look for the data, but then you can access it anywhere, anytime through your smartphones. And lastly, drones, which are replacing uh, the individual bridge workers by by using some ropes and truck buckets in order to reach the accessible regions. But drones have been very useful, as they can go to inaccessible location of the bridges, and they can also provide very, because nowadays high definition cameras are also installed in the drones, and it's just operating the drones, and we can already see very good clarity of the pictures of the region of interest, and later used for analysis. So all these techniques looks very promising for SHM in future. And I am also providing you here some of the uh, which is very good guidebooks for structural health monitoring of large civil structures and structural health monitoring of civil infrastructure systems, and also a major guidebook for acoustic emission testing. And all the three books provides very good review of the applications of different SHM systems on different bridge monitoring techniques. So thank you for your attention, and if you want to connect with me, I'm showing you here my LinkedIn barcode, and if you want to discuss anything, then you are always welcome. Thank you.
Vivek, have you any questions, Vivek?
Yes, sir. So first of all, I thank Dr. Naveen for having nice presentation. And when we see the comments from the YouTube, everybody has appreciated, and they told like a very nice presentation and informative. First of all, I thank you for that. Then there are some questions. So what I'll do is I'll just read out those things. You can answer that.
Yep.
So first question is, which kind of monitoring gives almost accurate results? You have mentioned vibration-based, strain-based, or acoustic emission method.
For this, I would say all the three monitoring methods are equally good, but it depends on what you are looking from the bridge structure. If you are looking for internal damages in the structure, then I would say acoustic emission is good, because you can already detect the damage before it is visible. And if you are just looking for deflections, then strain gauges. There are different types of strain gauges, as I have shown in my slides. But basically nowadays fiber optic sensors are widely used along with the normal strain gauges, and they can easily provide you information about the deflections. And if you are looking for acceleration, and then vibration based accelerometers are applicable. So it depends on what exactly, or what exact information do you want from these structures.
Okay, thank you, sir. I'll read the next question. What is the software used to study acoustic emission in structures?
There are two different softwares which are widely used. First one is Valence system, which is developed in Germany, and second one is Mistras, and it is developed in Greece. So these are two widely used softwares that are used for acoustic emission.
Okay, thank you, sir. Now, next question is, can acoustic emission Can acoustic emission monitoring predict the extent of damage?
Well, it can provide it can provide us the location sources, that is the position of the damage, but it cannot provide us the measurements of the damage length or the crack length. So basically, it gives us information about the detection, that is there is something happening within the structure. So it gives us as a warning system. And secondly, we can locate the exact geometric position of the damage. And thirdly, based on the analysis of the waveforms, we can classify these damages, whether it's a tensile crack or shear crack, that is if you are looking for very in-depth analysis of cracks, or else it's just the location and the quantification of the damages.
Okay, thank you, sir. Now, Pramod sir, any more questions are there? Hello, Pramod sir.
Okay. Vivek, can I speak?
Yes, sir. Yes, sir. Sir, you now I'll invite our beloved HOD, Dr. P. Prakash sir, to give the vote of thanks for the entire program, and also to Dr. Naveen Shetty.
Thank you, Dr. Naveen Shetty. It's very nice of you to have presented a fine paper. And actually, it is very beneficial to our lot of students here and many of the doctoral working students here. Apart from that, the structural health monitoring, many of them are online. I can see quite a few of them. Around about 412 people are online watching your and they are very appreciative. Thank you very much. Mr. Naveen. As you know, this program workshop was done on respecting the EEG Gesto on his first death anniversary. So this has been well appreciated worldwide, and all the speakers have done a fantastic job, starting from Dr. Ramachandra sir, who gave a fantastic lecture, and then and ended up with you with a fantastic lecture on health monitoring of bridges, which is very much a part of the highway structures. Thank you very much, sir, Naveen. And take care and be careful with your madam and at Brussels. Okay, thank you.
Thank you, sir.
Thank you. And I would like to conclude this workshop saying thank you very much. All of you be safe and take care of yourself. And all the presentation papers are available in YouTube. You please contact Dr. Vivek Das and also my dear colleague Pramod BV, who will be assisting you. Apart from that, we'll be issuing the certificates for all the participations and all the participants who have attended all the sessions would be definitely be given the certificate. Okay, we have got all the data here and we will take care of it. Thank you very much, sir. Thank you very much, everybody.
Thank you.
Thank you.